Slaves. All right. And remember yesterday I went through hydrogenation. Anybody happen to look at a stick of butter, margarine, or vegetable oil and think that's a saponifiable lipid, which means, in other words, it contains an ester? If you look at vegetable oil, if you had salad dressing, you're putting an ester, actually a triglyceride triester. All right. It's time for me to teach you how to get clean. And like I said, this course covers everything. My world of organic chemistry is your world. And there are a few things I would like you to leave my class knowing. And this is one of them. How do you get your hands clean? How does soap work? Well, soap works because of what's called surfactants, which are shorthand for surface active agents. And by the way, the switch is really on. And a surface active agent are chemicals that interact or work at the surfaces of things. What are surfaces of things? Things would be like your hand, your skin, and dirt. Water and your skin and dirt, those are all, think of different surfaces. And how do you get them to interact? Well, I think you know the answer to that. You use soap. If I had some dirt on my hands, how do I clean it off? If I were to take my hands, which are dirty, they're not, but assume they were, put them under water and do this, guess what? They would be still dirty. Or worse yet, if I had grease on my hands and put it on my underwater, go like this, no soap, they'd still be greasy. So how do you get it off? You use soap. Well, what is soap? Soap is a surfactant. And all soaps and many surfactants have a similar structure, something with a long non-polar tail and a polar head. Now, what is this polar, non-polar? Well, in order to understand that, I have to teach you about what's called a rule of thumb. And a rule of thumb is something that's most of the time like 95% true, but never 100%. If it was 100%, we'd call it a law. And that important rule of thumb that I want to talk about is like dissolves like. And if you notice, I wrote it in big font because it's that important. And like dissolve like means things that are certain polarity are soluble in other polarity, which are two types, polar and non-polar. So things that are polar are soluble in polar things. Things that are non-polar are soluble in non-polar things, like dissolves like. But things that are different are not soluble. Well, let's take a look at this. What's polar? What are some polar things? The most polar substance in all of nature or chemistry is water. And by the way, before I forget, if you weren't here yesterday, after class, make sure you pick up your test. I have them do. All right, so we have water is polar. Oh, it's something else. The shorter alcohols are polar, and then most salts are polar. Not all, but most, and that's why this is a rule of thumb, not a law. Example, sodium chloride, table salt, very polar. Now, what are things that are non-polar? Well, one that you're familiar with, vegetable oil. You take vegetable oil and water and shake it up, what happens? It separates because of like dissolves like. They're not the same polarity. One's polar, one's non-polar. What would be another one? Baby oil is non-polar. And let's get to some important things. What else is non-polar? Dirt. What else is non-polar? Grease. And that's why you can't get dirt or grease off your hands easily with just plain water. Because one's polar, one's non-polar. Like dissolve like tells you they're not going to dissolve each other or interact. And, oh, that reminds me, years ago I was watching, I think it was a cable show or something, a commercial comes on for detergent, and it was obviously done by, those Madison Avenue, marketing people who don't know much about the science of their product. And I almost fell off my chair laughing because they said, and our product even cleans greasy dirt. And I'm thinking, all right, greasy dirt. What's that? Well, it cleans it. But anyways, yeah, polar, non-polar. Water is polar, dirt and grease is non-polar. Now, this is stuff you should know leaving my class. Hint, big hint. Let's magnify that piece of dirt on my hand. There's a little piece of dirt here on my hand. We've magnified it. And if you take water's going to say, you're non-polar, I'm polar. I know like dissolves like. I'm not going to dissolve you. It's still on your hand. So what do you use? Soap. Now soap, as you see over here, is non-polar tail and polar head. And surfactants usually have this type of structure. This can be ionic or anionic. There are a few non-ionic surfactants, but they're rare. And one of the most important surfactants for cleaning is soap. And soap, you take your bar of soap, you go like this with the water in your dirty hands, you go like this, and the molecules of soap look at the dirt and say, oh, you're polar, non-polar, I'm non-polar, I know. Like dissolves like, my non-polar tail is going to be attracted to you. And not just one molecule, but many. And why? Because the non-polar tail is attracted to the non-polar dirt. Now, if you had bought the book, you would see in the page, when I have it here on the next slide, aren't you glad you saved some money? This is what it looks like. The inside here, they cut off a part so you can look inside. You have a piece of dirt. And you have the tails, like I have, going there all around it. So it totally surrounds the dirt. And when this forms, this is called a micelle. You should know what a micelle is. And a micelle is a dirt particle surrounded by soap molecules. Well, if you look at what happens with the micelle, what's on the outside of the micelle? Negative charge, the polar heads. And if you look at that, and your water molecule, you look at the micelle and you come over here, and the dirt particle is inside, totally surrounded by the soap molecules with the polar head on the outside, and the water says, oh, micelle, you're polar, I'm polar, like dissolves like, and let's go down the drain together. And lo and behold, my hands are clean. And that's how soap works. And for bar soap, the surfactant is a carboxylate anion. and it's made from fat and oils, mainly animal fat, which means it's sodium stearate, sodium oleate, which means R plus the carbonyl carbon is 18 carbons, long nonpolar tail, and notice this is ionic polar head, and that's your bar soap. And it's time, once again, for Dr. White's show and tell. How basic can you get? A bar of soap. Is that organic chemistry? Yes. Now, if you look at the bar of soap and at the ingredients, and the first one is soap. Well, that tells me a lot, but let's look at the different things in this bracket here. Sodium cocoate, that comes from coconut oil, and that's usually 1214. And you know OAT ending, carboxylate anion, metal in the front or element is this. So the sodium cocoate is when this plus this is about 14, 16 carbons, long, non-polar tail, polar head. As we go along, we have other palm kernel, and palmitate is 16. Now, sodium tallate is the way of being lazy, which organic chemists are, and so people on soap bars. You take tallow, beef fat, and what do you get mostly? You get mostly sodium stearate and sodium oleate. And a way of saying that is a sodium tallate. Now, there's some water, cal, and there's some unreacted fatty acids, which is why they put that down there. Then there's PEG-6 methyl ether, and what is that? Taking methanol reacted with 6 moles of ethylene glycol to help make a solid bar. You have a fragrance, you have glycerin, which is left over, a little in there. Why do they put sorbitol in there? To make it sweet. It could be also hydrogen bonding to keep it together. Sodium chloride, when they're making it, helps the viscosity of thicken it up. The next one is a preservative. The next one is a preservative, titanium dioxide, which is inorganic, is a white pigment. And all these things, really, what this is soap, which is really a carboxylate anion. And that's how soap works. And I'd like to go through it again, because this is one of those things I would like you to leave my class knowing. How does soap work? Let's go through it again. You have dirt, and when you think about dirt and what you're trying to clean the dirt with, water, you need to know about, and this is the whole key to the puzzle, like dissolves like. Notice I got it on the board not once but twice in big font. And like dissolve like means something that's polar is soluble in polar things, something that's non-polar soluble in non-polar things, things that are not the same polarity are insoluble. And as we look over here, the most important thing, water is polar. And if we look over in this list, the most important things, dirt and grease, are non-polar. So how do you get it off? You use soap, which has a non-polar tail, polar head. And now if we come over to our piece of dirt that's on my hand or your hand, or it could be on your clothing, could be when you wash your floor, wash your car, wash your hair, whatever, this all works the same. In fact, this morning when I was washing my hands, I was thinking, and I did, oh look, I'm making micelles. And what happens is you take and wash your hands like this with soap and water, unless you do it differently, I don't know like this, but anyways, look how it's Bad Humor Tuesday. And the dirt molecules, because like dissolves like, and it has a non-polar tail, is attracted to dirt. The polar head is on the outside. This forms, this whole thing is called a micelle. And water now sees only the polar heads of the micelle and says, I'm polar, micelle, you're polar, let's go down and drain together because light dissolves light. And you should know that. Now, there are other surfactants that are used for cleaning, and oh, that reminds me, I think it was last year, or maybe 3 semesters ago, maybe 4, a student came in with a copy or a picture of an ad from a magazine, and it was called, was it Micellar Water? Have you ever heard of that product? From what I've been told, it's quite a good product. People like to buy it. When I saw that name, I started laughing when I read contains micelles. I'm saying, no, that doesn't. It contains soap. The micelles aren't actually formed until you put it on your face, which I think that's where it's used, if my memory serves me correct. And it's amazing how advertising uses scientific terms, usually incorrectly. Now, if you ever wash your clothes, use a laundry detergent, which you don't use normally ever to wash your hands or your hair or stuff, but you use the clothes. And laundry detergents, which now if you understand organic chemistry, are made up of LAS, which is linear alkyl benzene sulfonate, and if you look here, what do we have? We have a benzene ring with an R group, which is from 9 to 12 carbons long. So this benzene ring and R is a nonpolar tail. And then you have the sulfonate, which is polar head. And this turns to work better in washing machines than bar soap. If you've ever seen old movies, how they used to clean clothes, you know, a scrub board, they put some bar soap on the clothes, go like this on the board, rinse it, and it would clean it. But in a washing machine, this works better. You know how to put an R group on a benzene ring for cross alkylation. You learn how to put a sulfonic acid group, which I can make into a sulfonate from aromatic. And this happened right after World War II when that chemistry was evolved. And then the advent of cheap oil and oil products, mainly benzene, that you can make into this, and this works good. And just about every laundry detergent, this is the molecule that really does the cleaning. There are other additives that differentiate different brands. All right, I'm going to turn the switch off real quick. There are other types of surfactants. One is called a phosphoacylglyceride. It's a triglyceride of a diglyceride of glycerin or glycerol. Let me show you a better picture. Again, switches off. And this is an example, don't copy this down, of a phospholipid, they're also called. And notice here I have a polar head and 2 long chains coming out, what it really looks like. where here you have the polar head, and here R is 16 to 18 carbons long. Here they show a stearate. And these are called phospholipids. This one in particular is called lecithin. And they're surfactants. Mother Nature uses surfactants in many things. Lecithin, and again switches off, is phospholipid. It's found in egg yolks. By the way, the structure I just had on the board, this thing, is yellow. Have you ever seen an egg yolk? You wonder why it's yellow? Because of the phospholipid in there. And it's also found in soybeans. Now, one of the things phospholipids have an interesting effect on is your brain and other parts of your body. And it's found in soybeans. And when I get back to eating soybeans, which I have been, I sleep better and I feel my mind is working better because of the lecithin. That's my personal opinion. Now, how many of you are familiar with a product called mayonnaise? And what is mayonnaise? I see at least one person. It's water and vegetable oil mixed together. Wait. Yeah, it's not separate. They're all together in what we call an emulsion. How does that happen? Well, the classic way of making mayonnaise is water, vegetable oil, egg, and some lemon, and some seasoning. And what is the egg or egg yolk used for? It's used for the lecithin as a surfactant to help bring the water and the oil together into a stable emulsion. And a lot of things you have that look like mayonnaise in personal care products, hand cream lotions and all that, use surfactants to bring together water with different things like oils to stay stable to use on your hand. All right. Now, if you remember at the beginning of the chapter, I talked about switches on now. Through the miracle of modern computers, I talked about lipids. There are two types. Saponifiable lipids you learned were fats and oils. And those reacted with base and water to give carboxylate anions. Now, there was another group of lipids. These are molecules that come from things that are or were alive. And they're not soluble in water, soluble in non-polar things. And the other type is non-saponifiable lipids. And those do not undergo hydrolysis reactions. In other words, no reaction. Well, what are non-saponifiable lipids? Those are your steroids, which are also known as your hormones. Now, if you look at any of your steroids in your body that Mother Nature has created, they all have the same basic ring skeleton. You have a 6-membered ring, and then it shares 2 carbons, and we call that a fused ring system. I stayed away from it in this class, even though I could have talked about it. Right next door here, 6-membered ring. Then right here on the top, going up, you have another 6-membered ring. And then right next door, sharing 2 carbons, you have a 5-membered ring. And this is a steroid. 4 rings, 1, 2, 3, 4, connect together. Every steroid has this ring system. I would like you to know how to draw the ring system of a steroid. Again, 6, 6, 6, 5. And I won't ask you to learn it, but they're called A, B, C, and D rings for people with steroids. My research group in graduate school, half our group worked with steroids, the other worked which was called sesquiterpenes. I worked in the sesquiterpenes, and those are also complex ring systems. Now, one of the questions I keep on telling you to ask is, why am I learning this stuff? with me. One more to go. What am I going to talk about right now is this organic chemistry. In no way am I implying you should or shouldn't use any of these or think about it the way I do or don't. All right. If we look at the molecule switches off, you don't have to know the structure, but I just want to point out something real quick. This is progesterone. It's a female hormone, important one. And if you notice, it has the same 4 rings, 6, 6, 6, 5. This wedge means the methyl group coming toward you, hydrogen going back, hydrogen's methyl. That ketone is coming toward you. Notice progesterone has a ketone in this ring, double bond, ketone up there. Now, important male hormone for steroid is testosterone. And testosterone also has, and again, you don't have to write this down, I'll never ask on a test, either CHS, 6665. Like progesterone, it has ketone here, same place, double bond, methyls, but instead of a ketone on the 5 ring, it has an alcohol. So let's take a look at this. Progesterone, female hormone, ketone, male hormone, alcohol. Doesn't that explain the difference between men and women? Men are alcohols, women are ketones. That failed miserably. All right. Now, an important female hormone, another one, is estradiol. And if you notice, it has the same ring system, 6665. But here now you have a benzene ring with a hydroxyl group, phenolic ring. You have alcohol up there. Estradiol is the hormone that regulates a woman's monthly cycle by how much is in your body, and I'm sure you've learned this in other classes or will, controls that. Well, this is a very expensive molecule to make or obtain. But somehow, organic chemists working with medical science found out that if you take a cheap molecule with a ketone, react it in a Grignard-like reaction, and make this, which is very similar, instead of having an alcohol, it has an alcohol plus a triple bond, which is made in a Grignard-like reaction with a ketone up there from a molecule I can get cheaply from a plant, extract. I can now make this, and this is called ethinyl estradiol. Common names, these are not IUPAC names. There are for those, and this is the molecule that's the active ingredient in birth control pills. Whether you believe in them or not, birth control pills have had a major effect on life on our planet because it's given women who want to control over their body in the way they want to. And that's because this is available cheaply. And what they do in birth control pills is regulate the amount of ethinyl estradiol in the pills and match it to how normally your monthly cycle would be, and that stops you from getting pregnant because your level doesn't change. And for some reason, a woman's body thinks this is identical to this, and it interprets this as being really this. And that's how birth control pills work. But you never thought I'd get into that in this class. I get into everything in organic chemistry. Hopefully not trouble them. All right. Let's see, today is Tuesday. How many people think by Thursday they'd be able to take a look and work on the, better yet, let's do it Monday. Monday I'll be going through the fats and oils problem set, lipids, oils. All right, new chapter. Switches off on this slide, but I just want to do a couple things. In this new chapter, we'll be talking about carbohydrates. It's going to be really sweet. Watch out, it can be very fattening, I know, unfortunately. And I'll get into some stuff you didn't think I could get into, but by now you know I can. And let's talk about carbohydrates. Before I talk about carbohydrates, what we're really getting into a little is biochemistry. And biochemistry, I won't ever put this on a test in the ACS, doesn't study a chemical substance found in living things and the chemical interactions, in other words, chemistry of those substances, in other words, chemicals. And one of the things people do, and I don't know why, as a synthetic organic chemist, I always find it strange, is as soon as some chemicals are in your body, they go, ooh, magic, ooh, strange things. No, that's the same organic chemistry I've taught you, and that's why I have the functional group chemistry that you've learned for organic molecules occurred this the same way in bioorganic molecules. You have an aldehyde, it's going to react like aldehydes. A ketone reacts like ketones, etc. And in other words, the functional group chemistry going on in your body is the same as what we've studied. And if you look at a biochemical substance, people say, ooh, this is magic. No, it's an organic molecule, but it's very complex organic molecule. Same thing with enzymes. Enzymes are just very fancy catalysts. And a lot of the enzymes are really a way Mother Nature can very selectively provide H+, which you see me do all the time on class. All right, switch is on. Don't draw the structures, but the switch is on. Let's talk about carbohydrates. What is a carbohydrate? You should know a carbohydrate is a polyhydroxyl aldehyde or a polyhydroxyl ketone or a compound that yields such upon hydrolysis. Now, poly means many, hydroxyl, OH. What's an aldehyde and ketone? You learned that for test number 2. Now, I will never ask on test what's the structure of glucose or fructose, so you don't have to learn that, but I'll be using it. And let me talk about something which I'll go into detail later on, and that is a Fisher projection. This is called a Fisher projection. Every intersection of a line is a carbon. Carbon here, 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 carbon there. And you also show some like that. Now, another thing I need to talk about when I talked about aldehydes, I showed you this structure, carbonyl, hydrogen, R group, aldehyde. You learned how to name them, you learned how they reacted, you learned how to make them. Now, at the time, if you go back and look at the slide when I first introduced you to the aldehyde structure, I said carbohydrate chemists write it like this, which I usually don't. These are both representations of aldehydes. My software, and if you go on the internet, when you see carbohydrates, you'll see the aldehyde written like this, which is the same as this, but this is easier for software to do. And if you notice in glucose, I have at the very top an aldehyde. And then notice one hydroxyl group or alcohol, 2, 3, 4, 5, polyhydroxyl aldehyde. Glucose, which we'll learn later on, is the most abundant carbohydrate in nature, or sugar it's also called, is the sugar in your blood. And you don't have to know the structure. Now, that's a polyhydroxyl aldehyde. Here, notice, carbon, double bond to oxygen, carbon there, carbon there. And that, as you learned for test number 2, is a ketone. This is called fructose. How many of you have heard of, in many products that you buy now, has high fructose corn syrup? And that's the structure. You do not have to know the structure of fructose. But if you notice, I have carbon here, lines intersection, this main is a carbon, carbonyl, the carbons there, and therefore this is a ketone. And then I have hydroxyl group, alcohol, hydroxyl group, hydroxyl group, hydroxyl, 5 of them. So this is a poly, many hydroxyl ketone, which means it's a carbohydrate. Now remember, what you think of carbs, like in food, is different than the definition that science uses, because sugars and things like this, monosaccharides you'll learn, are also carbohydrates. You usually think of carbohydrates as things like starches, which is also a carbohydrate. Because the starch, upon hydrolysis, reaction with water and a catalyst, will give you glucose. All right, I'm turning the switch off. And I'm just doing this because you might have this in other classes. And I want them not to be able to say, did you learn that in organic chemistry? But we covered it briefly. All right, I am not, and I'll admit this, a carbohydrate chemist. I haven't done any work in there in the lab. I've done it in my kitchen, but not in the lab. And also in restaurants too, consuming carbohydrates. But let's talk about it. Monosaccharide, carbohydrate that contains a single polyhydroxyaldehyde or ketone, glucose and fructose are monosaccharides. And I might be pronouncing some of these words because, again, I have worked in this area. Oligosaccharide, you don't have to know, but that's a carbohydrate contains from 2 to 10 monosaccharides. Why they have to come up with a term like that, don't know. All right, let's move on to the next slide. Again, switches off. Now, there's a special oligosaccharide, which is called a disaccharide, which I would like you to know the name of, and that is sucrose. Sucrose is 2 monosaccharides connect together. We'll talk about the structure later. Sucrose is a common name, and you know as an even commoner name, table sugar or sugar. You know the white stuff you put in your coffee, tea, or on your cereal, or when you bake into your baked goods to make it taste sweet. That's a disaccharide. All right. And you should know sucrose is table sugar, a disaccharide. Switches off, polysaccharides, polys means many. When you have a lot of monosaccharides hooked together in what we call a polymer, like a freight train, we call those polysaccharides, and you also know them as starches, which I will not ask on the test. Now, before I move on with carbohydrates, I need to talk about an important area, which up to this point I've stayed away from, and that's called chirality. Chirality, which is, for those of you reading the book, chapter 5, which I skipped. Anybody reading the book? Aren't you glad I saved you all that money? But anyways, chirality means handedness. And chiral is the Greek term, Greek word for handedness. And what was it, last summer in my 12-12 class here, I had 2 people who were from Greece and were fluent in Greek, and they confirmed that was true. Even though I'd only seen it in books, now I know it's true for real, from actual Greeks. Anyways, chirality means handedness. And it turns out many molecules, including a lot of the carbohydrates, like all of them almost, exist like your hands, right and left form. And notice this is different from this, and I'll be teaching you that. Oh, I got plenty of time to do it. Now, in order to talk about chirality, handedness, I need to talk about mirrors and mirror images. I'm going to assume everyone in this class at one time in your life has stood in front of a mirror and seen your image. Now, I'll have a homework assignment after a little while that I'll give you. Oh, I have an important warning to tell you. This is the part of the chapter and semester you'll learn for sure why Dr. White should never ever think of going to art school. All right, let's take a sewing needle. Sewing needle, pointy end, metal shaft, hole at the end, you put the thread through. Like I said, I'm not going to art school. If I were to take a sewing needle and put it in front of a mirror, and I'm going to put an artificial mirror in there, what am I going to see? The mirror image. And if you don't believe me, try this at home with a sewing needle. Be careful, it's one end is sharp. And you'll see that. And if I could pick the mirror image off out of the mirror, I could lay it over this sewing needle and push the 2 together. And everything would line up. And that would mean it's got a superimposable mirror image. And so things that you can take the mirror image and push it together, and so everything lines up, is called a superimposable mirror image. A number of years ago, when I was doing this slide, and I've been doing it a couple of years, one of the students, remember I told you the first day I was always the first one down in the spelling bee, and the student said, you know, you got that spelled wrong. And I said, what do I have? Super impossible. Oh, that's why students are having trouble with this part. But let's take another one. If you were to take a red rubber ball, those of you know music titles, there's the name of a song like that, and put it in front of some plain red rubber ball in front of a mirror, you'd see the mirror image. You could pick it up and push the two together. Every point would coincide, so it'd be superimposable. Now, the other type of mirror image is non-superimposable mirror image. Remember, it switches on now. And I don't need a mirror because I can do it right now. What do I have here? My right hand. Pretend my ring isn't on. If I take my right hand, and there's a mirror right here, what am I going to see in the mirror? My left hand. The reflection will be my left hand. Oh, quick time out. Does everybody know what this is? Spider doing push-ups on a mirror. Never mind. All right, now, here's my right hand. Here's the mirror image. Again, no ring on there. Are they superimposable? All right, I'll take my middle finger and push them together. So, wait a second, my thumbs aren't lining up. The other fingers aren't. All right, I'll do my thumb. Oh, those aren't lining up. I'll do my pinky. I think they still call that the pinky, right? And so my hands are mirror images. And here's the homework assignment. When you have a chance, stand in front of a mirror and hold up one of your hands, and you'll see your other hand. You'll see I'm not lying to you. I'm actually telling you the truth. So your hands are mirror images, but they're non-superimposable. Turns out your feet are the same way, my shoes are, and many things are non-superimposable mirror images. And that leads us to where we're going now, chirality. And chirality, you're going to look at things, objects or molecules. Let's look at objects first. There are two types of objects in the world. Chiral objects, achiral objects. Chiral objects, remember, chiral means handedness, and that's why they picked that name. I'm glad they didn't pick the Greek word for footedness. But anyways, chiral object, you should know, I won't ask on a test, but I will ask you to be able to identify object, is an object that has a non-superimposable mirror image. Chiral object, non-superimposable mirror image. So that means my hands are chiral objects, because they're mirror images, non-superimposable. My feet are chiral, mirror images, and if you don't believe me, stand in front of a mirror and put your one foot in front, you'll see the reflection of your other foot. And trust me, they're not superimposable. I got my big toe over big toe, the rest of the foot doesn't line up. So now we have what happens when you have something with a superimposable mirror image. In other words, it has identical, like a sewing needle, red rubber ball. We call these achiral. The letter A as a prefix means without. So that means it doesn't have handedness. It's got a superimposable mirror image. By the way, I worked for someone who was amoral. Not immoral, amoral. And he was a very dangerous person because he had no moral compass whatsoever. Very nice person, but you had to watch him sometime because he'd do the strangest things because he just had no moral compass. He was amoral. But we're talking about achiral. So if I ask on a test, the following object is a chiral or achiral? Chiral, non-superimposable mirror image. Achiral, superimposable mirror image. If I put down sewing needle, the answer would be achiral. If I put down a red rubber ball, the answer would be achiral. Ooh, this is fun. Let's try another one. How am I doing time-wise? Plenty of time. All right, let's look at the following. Say sometime in the future, 3 points each is the following. An achiral or chiral object, I put in hand. A, your right foot. Well, you can look at this and say, my right foot, its mirror image is left foot, they're non-superimposable. That tells me it's chiral, non-superimposable mirror image. You guys keep a secret? If something has in an object, right or left, that immediately tells you it's chiral. So if I were to say, is my right winter glove chiral? And the answer would be yes. Now, let's look at this. A plain white tube sock that has no toes. You know how some of the women's tube socks have little toes on the end? Well, this one doesn't. Well, is that chiral or non-chiral? Well, the traditional way is, there's my sock. Again, this is the part of the semester you know I'm not going to go to art school. Yep, that's a sock, tube sock. Mirror image. Since it has no toes or writing on it, I can pick this up, rotate it, push the two together, everything lines up. And therefore, this would be achiral. And if you don't believe me, you have plain white tube socks. Can you put them on either feet? And the answer is yes, because they're achiral. Can you put your shoes on either feet? And the answer is no, because they're chiral. It turns out molecules interact that way with chiral and achiral. Ooh, let's do one more. It'll be a hard one. We can get personal now. My pants. Is my pants chiral or achiral? Well, if you did the mirror image, and don't forget the button and the zipper, you would find it's non-superimposable. But an easier way of thinking about that is right pant leg, left pant leg. Are they different? Well, you better believe it. If I put my right leg in the left pant and wore it that way to class here, I think somebody might call the police and get help from me. But my zipper and everything would be in the back, my back pockets would be here, and I don't think it would feel right either. So your pants, like these, are chiral. So with that, I'm going to end the whole 35 seconds early. Quick